America built a fighter plane out of magnesium, extremely flammable magnesium. The metal that ignites when you look at it wrong and burns white-hot until there's nothing left but ash. And they used more than a little bit. They built the entire fuselage out of it. The Northrop XP-56 Black Bullet, a tailless interceptor designed to chase down Nazi jets at 465 miles per hour and 25,000 feet. A machine so radical it looked like it flew in from the future, and so unstable it tried to kill everyone who touched it. The story of the Black Bullet comes down to this: the Polo helmet that saved the test pilot's life, the welding technique that changed manufacturing forever, and the 10 flights that proved speed means nothing when the plane wants to fly upside down and backwards. 1940. Jack Northrop walks into a U.S. Army Air Corps briefing room with a proposal. The Model N2B. No tail. No drag. Just a bullet-shaped fuselage, stubby wings, and a pusher propeller mounted in the back. Not a flying wing, despite what people assume today. A flying wing has no fuselage at all, just a single continuous airfoil. The N2B kept a distinct, bullet-shaped body housing the pilot and engine, which is exactly where the nickname came from. Not the paint job. The first prototype rolled out in bare, unpainted silver metal. The design promised to outrun anything the Luftwaffe could throw at the Allies by eliminating the tail entirely, cutting drag, and letting the whole airframe act like a dart. The generals looked at the blueprints and saw the future of aerial combat. But there was a problem: aluminum. The military was convinced a wartime shortage was coming. Every bomber, every fighter, every transport plane was going to need aluminum. Production lines across the country were already competing for the same raw material, and the War Department had no interest in grounding a fleet because of a supply bottleneck. If the supply dried up, the entire war effort would stall. So they made a decision that still baffles engineers today: build it out of magnesium instead. Magnesium is 33% lighter than aluminum. 33%. That's a large advantage in a dogfight. Lighter means faster. Lighter means more agile. Lighter means you get the jump on the enemy before they even know you're there. On paper, it was the kind of number that wins wars. It also means you're flying a bomb. Magnesium detonates. One spark, one stray bullet, one overheated rivet, and the entire airframe turns into a self-sustaining inferno that water can't touch. Pour water on burning magnesium and it reacts with the flames, releasing hydrogen gas and making the fire worse, not better. Firefighters have to smother it with dry sand or specialized extinguishers, and even then it can keep burning at temperatures north of 5,000 degrees Fahrenheit. The Army knew this. Northrop knew this. They built it anyway, because in 1940, stopping the Nazis mattered more than the fine print. The magnesium presented an immediate engineering nightmare. You can't weld magnesium with traditional methods. The heat triggers a chain reaction. The metal ignites. The weld explodes. Your fuselage becomes a fireball before the first rivet goes in. Standard arc welding exposes molten metal to open air, and magnesium in that state instantly combusts. Northrop engineer Russell Meredith solved it in 1941. He patented Heliarc welding. Inert helium gas floods the weld zone, choking out oxygen and preventing ignition. A tungsten electrode strikes the arc while the helium blankets the molten pool, keeping it stable long enough to fuse without catching fire. The magnesium stays stable. The fuselage holds together. The plane doesn't explode on the assembly line. Heliarc welding saved the XP-56 and reshaped manufacturing. The technique evolved into TIG welding, the industry standard today for aluminum, titanium, and magnesium fabrication. Every modern aircraft, every spacecraft, every high-performance race car owes its existence to the process Russell Meredith invented to keep the Black Bullet from self-immolating in the factory. The Apollo lunar module was TIG welded. The SR-71 Blackbird was TIG welded. A fix invented to stop one doomed prototype from catching fire ended up underpinning almost every high-performance metal structure built since. The XP-56 program was supposed to save the war. It couldn't even save itself. February 13, 1942. The U.S. Army Air Forces orders a second prototype despite mounting evidence that the design is aerodynamically broken. No tail means no vertical stabilizer. No vertical stabilizer means nothing to counteract yaw. And yaw in a tailless aircraft means the nose whips sideways without warning, hurling the pilot into a spin he can't recover from. Wind tunnel data was already flagging directional instability, but the program had momentum, funding, and a war to win. Nobody wanted to be the one who killed it on paper. The engineers knew. The test data screamed it. They built the second prototype anyway, late March 1943. The first engine run. The Pratt & Whitney R2800-29 roars to life, all 2,000 horsepower hammering through the propeller shaft. This wasn't an underpowered airplane. The R2800 was one of the most capable radial engines of the war, same family that powered the F-4U Corsair and the P-47 Thunderbolt. But cramming that much power into a pusher configuration meant an extended drive shaft running the length of the fuselage to reach the rear-mounted propeller. The shaft flexes, warps. The drive system collapses. The engine destroys itself in seconds. 5 months of delays, redesigns, reinforcements. And still, nobody asked the obvious question. If the engine can't handle the stress on the ground, what happens when it's airborne? April 6, 1943. High-speed taxi tests begin on Muroc Dry Lake, the same dry lake bed that would later host early jet and rocket plane testing. Chief Test Pilot John Myers straps in, throttles up, and immediately feels the nose yank hard to the left. The yaw is violent, erratic, unpredictable. The plane doesn't want to go straight. It wants to swap ends and cartwheel across the lake bed. Myers shuts it down and climbs out. He tells the engineers the plane isn't ready. They tell him to keep testing. September 30th, 1943. First flight. Serial number 41-786. John Myers lifts the first prototype off the ground. 5 feet. That's it. 5 feet of altitude before he slams it back down and hits the brakes. The plane is so nose-heavy and unstable that even lifting the wheels feels like wrestling a live grenade. He lands. He survives. October 8th, 1943. Another taxi test. 130 miles per hour across Muroc Dry Lake. The left main tire explodes. The nose digs in. The tail flips up. The entire magnesium fuselage somersaults, shreds, and disintegrates in a cloud of metal and dust. John Myers is thrown clear. He hits the ground hard. And the improvised polo player's helmet he's wearing, instead of standard headgear, absorbs the impact and keeps his skull intact. He'd suspected for weeks that the first prototype was a flying death trap, and he'd quietly swapped his regulation flight helmet for something with more padding. Standard issue headgear at the time offered minimal impact protection. The polo helmet, thicker and built to absorb blunt force, did the job standard gear wasn't designed to do. Crawling out of the wreckage, Myers delivers the most understated crash report in aviation history. The airplane wanted to fly upside down and backwards, and finally did. That's it. That's the whole story. The first prototype is gone. The pilot survives because he didn't trust the plane enough to wear the regulation helmet. And the program continues anyway. March 23rd, 1944. The second prototype, serial number 42-38353, flies for the first time. This one has modifications. A huge tail fin bolted to the back to try to force some directional stability into a design that never had any. Wingtip air bellows that inflate and deflate to counteract yaw, essentially crude pneumatic control surfaces reacting to airflow instead of pilot input. Band-aid fixes on a fundamentally broken design. It flies. Barely. The tail fin adds weight. The air bellows add drag. The top speed the plane was supposed to hit? 465 miles per hour at 25,000 feet. That number came straight from Northrop's original pitch, the whole reason the Army greenlit the project in the first place. The actual speed pilot Harry Crosby manages to coax out of it? 250 miles per hour in level flight, burning fuel like a freight train and fighting tail heaviness the entire way. Less than half the promised speed from a plane that was supposed to be the fastest interceptor in the sky. If this sounds like a bold experiment turning into a disaster, take a second to hit like. It helps the algorithm show this to more people who need to see just how badly wartime desperation can derail engineering. 10 flights. That's all the second prototype survives before the military declares it completely unairworthy. August 1944. Harry Crosby lands the plane for the last time and files a report that reads like an autopsy. Tail heavy on the ground, starved of power in the air, even with 2,000 horsepower up front, because the thick wings and constant yaw correction bled off every bit of thrust before it turned into speed. Guzzling fuel at a rate that makes long-range interception impossible, and still trying to swap ends every time the throttle changes. The Army Air Forces grounds it, permanently. 1946. The XP-56 program is officially canceled. The piston pusher design is obsolete. Jet fighters like the P-80 Shooting Star are already flying, making a temperamental propeller-driven interceptor irrelevant before it ever got close to a production line. The Black Bullet is dead. 2 prototypes built. 10 total flights. 0 combat missions. 1 pilot saved by a Polo helmet. And 1 welding technique that changed manufacturing forever. So what do you call a project like this? A failure? Yes. The plane was a death trap that couldn't fly straight, couldn't hit its speed targets, and couldn't survive a tire blowout without killing the pilot. A waste of money? Probably. The military poured millions into a design that was aerodynamically broken from day one, chasing a tailless dream that the wind tunnel data had already warned them about. But failure isn't the whole story. The XP-56 failed as a fighter. No question. But the project succeeded in ways nobody predicted. Heliarc welding enabled aluminum fabrication at scale. It made supersonic jets possible. It put rockets into space. The Apollo lunar module? TIG welded. The SR-71 Blackbird? TIG welded. Every high-performance aircraft built in the last 80 years owes its existence to the technique Northrop invented to keep the Black Bullet from exploding in the factory. And that's the paradox. The plane was a disaster. The innovation was a triumph. The military bet on magnesium to solve an aluminum shortage that never came. They got a flying bomb that tried to kill its pilots. And they also got the welding process that built the future. Think about that. The worst fighter plane America ever built gave us the tool that made modern aviation possible. The project everyone calls a failure changed the industry forever. And the test pilot who survived the crash did it because he didn't trust the plane enough to follow the rules. Sometimes the real breakthrough is what you invent trying to keep the machine from killing you. The surviving second prototype sits in storage at the Smithsonian Institution's National Air and Space Museum. Not on display, not restored. Just tucked away in a warehouse somewhere, gathering dust, one of thousands of aircraft in the collection that will likely never see a public gallery. A reminder that not every radical idea works, and that sometimes the things we build to win a war teach us more in failure than they ever could in success. If any of this stuck with you, like and subscribe. There's so much more hiding in the wreckage of aviation history, and every single piece of it matters.